Thank you very much first for giving me the honor of opening this session. As you said, I'm Humanoid. I used to be a master's student at IEEE Zurich and I'm now working at Robotics. And today I will present our work on Planar Bipedal Locomotion with Nonlinear model predictive control, online gait generation using whole body dynamics, which was done as a collaboration between the Amber Lab at Caltech and the Robotic Systems Lab at IEEE Zurich. So in the beginning, I would like to quickly go over some related approaches. How has the dynamic locomotion problem been solved so far? On one hand, we have offline gait synthesis using the whole body dynamics, where I would like to quickly highlight the method of hybrid zero dynamics, which uses numerical optimization to find periodic trajectories of actuated outputs, which correspond to our actuated degrees of freedom, such that the unactuated degrees of freedom exhibit stable periodic behavior. So if this is possible to pre-compute stable periodic trajectories for walking. However, if you would like to have non-periodic trajectories, or also like to be able to react to feedback on the planning level, there is the method of online gait synthesis using model predictive control, where an infinite horizon optimal control problem is approximated in a receding horizon way. Due to the computational complexity of actually having to run the optimization online, these methods have so far been mainly limited to simplified or reduced model dynamics. So with this in mind, our contribution is threefold. First, I would like to propose a whole body nonlinear model predictive control approach that allows us to take the full system dynamics into account for online planning. Then, we show that we can reduce the computational cost of the presented approach by adding a hybrid zero dynamics reference and terminal cost, and then provide experimental validation at the example of the Planar bipedal robot Amber 3M. So with this we go directly to the MPC formulation, where we use reparameterization of the whole body dynamics. Here we basically exclude the inverse dynamics from the MPC prediction step. This is done by choosing the state vector x to be the generalized coordinates and generalized velocities. And the input vector u, or decision variable of the optimization problem, are the contact forces and the trunk accelerations, which importantly we choose to optimize over instead of optimizing over the joint force. So if you then take the derivative of our state vector x, we can see that almost all the components are already contained in our state or input vector, and the only thing that's left to compute is q_e, which are the base accelerations. Those can simply be obtained by looking at the dynamics formulation via Lagrange, expanding it to show the separated components for joints and base, and then just eliminating the lower half and taking the inverse of dBV, which is the part of the generalized mass matrix corresponding to the base. So what we see here is that with this approach, we can actually reduce the computational complexity of taking the whole body dynamics into account. Nonetheless, it's important to stress here that we don't have any loss of information due to this reparameterization, and we can recover the torques via inverse dynamics for every point along the horizon. So with this method, in short, we can focus our computation on the unactuated degrees of freedom, while still taking the whole body nonlinear dynamics and, if desired, constraints, such as, for example, actuation limit, into account. The presented MPC controller was then integrated together with a low-level controller that recovers the planned torques using inverse dynamics. And in addition, for the example of the robot Amber, also has a PD controller and a friction compensation module. The total torques are then sent to the robotic platforms, and we use an estimator to update our MPC and low-level controller with the estimated state. Furthermore, we assume the gait sequence, target base pose, and the reference trajectory are given. With this approach, we could then synthesize a wide range of different locomotion behaviors for different gait patterns, for walking forward, walking backward, different gait patterns, gait speeds, and also you can see now on the right side there's a gait pattern with actually a small double support phase. But in the bigger picture, since we're not only interested in getting this approach running on a bipedal robot, but we would actually like to see it applied on a 3D system eventually, we started to investigate how we can reduce the computational cost further through horizon shortening. So what we see on the left side is if you choose our MPC planning horizon to be sufficiently long, we actually get a reasonable approximation of the infinite horizon optimal control problem, And the more we shorten this horizon, the more important the cost to go becomes, and also getting a good approximation of this cost to go. So for all the results shown so far, we just used a very simple heuristic reference and terminal cost, as is visualized here. But now we would like to propose to replace that with an offline generated hybrid zero dynamics reference trajectory, which importantly, due to the periodic nature of HCD, can be used very well to give us a good approximation of the cost to go. We then compared this method with the new terminal against one method without the terminal and one with the heuristic terminal, which are visualized here. And there we could see that if we shorten the horizon, that actually the version with no terminal quickly destabilizes. And if we shorten the horizon even further to a very short 0.2 seconds, we can see that only the method with the hybrid zero dynamics terminal still manages to synthesize robust locomotion. For this last approach, we then benchmarked a few computational metrics for 10 ASCII iterations for different horizon lengths of the MPC. And we could show that we could achieve an MPC update rate of up to 850 Hz for the very short horizon of 0.2 seconds. And with this, it was possible to show that we can actually drastically reduce the computational complexity through adding this hybrid zero dynamics terminal cost. With this, I would like to present you now our method on the hardware, where you can see first the MPC with a heuristic reference reacting to a disturbance while stepping in place. And now during the forward walking, we can see how the robot actually slightly slips, but the control approach manages to stabilize the system and return to a stable walking behavior. Now these are the analog experiments for the MPC with the hybrid zero dynamics reference and the terminal cost, which achieved a particularly nice looking forward walking gait. With this, I come to my conclusion. First, we've seen this reparametrized whole-body nonlinear predictive control formulation that allows us to take the full system dynamics into account for planning. Then we could see that we could achieve significant horizon shortening and significant reduction of computational cost through adding this hybrid zero dynamics terminal. And then also we could provide one of the first hardware demonstrations of using the whole-body dynamics for online planning. Thank you for your attention. I'm looking forward to your questions.
Thank you for a nice presentation. So we can have a couple of questions from the audiences. Have any questions?
Hello. All right. Thanks for the interesting presentation. I have two simple questions. So the first one, at a higher level, what are your controller inputs? And the second question is, have you tried stepping on uneven terrain?
Thank you for the questions. So on the high level, the inputs can be seen in the diagram here. So basically the user selects a gait sequence that is given and can enter target base flows. Those are the only two inputs to the algorithm. And to your second question, no, we have not tried the approach yet on uneven ground, but I think it's what is particularly exciting here is that we have like this hybrid zero dynamics reference, which is periodic by nature. But if we combine that with an MPC, we can actually get non-periodic behavior, which is really what would be required for walking on uneven ground, especially I think in unstructured environments. Thank you.
And maybe one more question from audience. Okay, then please thank again Manuel for